Paul, you're muted.
Better?
Yep, there we go. Thank you.
Thank you. I'm not sure why it muted. That's really weird. So what I was saying, sorry about that, is we're going to take, and we alluded to this last class, which is we're going to model systems, no matter how complicated they are, and we can model them really basically just by looking at individual elements. And we're going to go ahead and have models of those. And then we're going to have this big system with all these models that are interconnecting. But what we're trying to do is assess the overall system. So it's much easier for us to take all those individual blocks and combine them into one. So the purpose of this sort of class, or this module, if you will, is how we'll do math to combine those systems. So we'll start off with this basic, very simple block diagram, which has an input and an output, and it has this transfer function G of S. Remember the rules for a transfer function. We ignore any initial conditions, and it just represents the system itself. It does not include any input. So it could be a unit step, it could be a sine wave, cosine wave, it doesn't matter. We also, and I don't use this all that often because I don't know, it doesn't seem like it saves that much time. But you can, which is a signal flow graph method, which is exactly the same, except you just represent your transfer function with an arrow showing the direction, right? Normally we go left to right, but we do have some feedback that we could be going from right to left. And it's the same idea. So you can use either one. I just have used block diagrams. That's the typical one. All right, so how do we go ahead and manipulate these three individual transfer functions that take an input and then they do their own thing, get an output, and then the output is actually the sum of those three individual outputs? Well, this one's pretty easy. We take a look and we've got our inputs, G1 times R plus G2 times R plus G3 times R. So hopefully what you see pretty quickly is our output is just going to be the sum of those three. Really, really, really simple one is adding blocks, or another way to say that is parallel blocks. So anytime you see a summing junction, you're essentially going to add those together. So now our simplified transfer function, which is what we can actually analyze, we replace the three individual blocks with the summing junction, and we simply combine those into one block representation. Series block, another way to say series block is that they're in cascade with each other. So if we look at the outputs, first one we have is the output of G1 is just R times G1 of S. Now that becomes the input to block G2. Now our output, our overall output is R G1, G2. So if we're going to replace that, we can just go ahead and put those in cascade, which essentially means multiply each other. So if you see two blocks in series, you're actually multiplying them together. Very different than resistors in series, right? A very different approach to doing things. This is just multiplying together. Anybody know why we can multiply our blocks together like this and not have any issues? Say it again.
When you that output over the input, the output is not the input, or the output it can well.
So you have
it creates a new data function. This output is from this output.
That's right. And so how did we actually say that, or why are we allowing that to say that?
Well, if R is 1 over S, multiply the G1 by 1 over S.
Yep, that's correct. But why are we allowed to say that?
Oh.
Remember how we started modeling equipment? We used op amps. What did we say that op amps do? The interstage loading, remember? It provides so that the output of one block goes to the input of the other, but the loading effect on that second block has no impact whatsoever on the output over here. So this one right here it goes in here, and whatever G2 of S is, it doesn't care. It always is going to put out whatever R times G1 of S is equal to. That's what's happening. In resistors, I don't have that loading. I load them down, right? So if I'm trying to calculate the current through here, that current looks very different than the current just through R1. So that's why you have, in this one, you could actually multiply them, where you'd have the same result if you did something like this, right? If you calculated a current and you built a block that would do something like this, and then you do the same thing over here. Now those two are not represented. They're not linked to each other directly. They're independent of each other. And so that's why in series, we get a very different configuration than in real world resistors. Okay. And most systems, this is what you want. Why do you want most systems like that? Because again, in almost any system, they're so complex that if you take all those pieces of equipment and you put them together and try to design something, it's very difficult to do that. But if you can neglect that loading between the stages, I can build stage A, then I can build stage B, then I can build stage D. See, I'm basically breaking down my system into smaller, more easily identifiable sections, and then I can actually go ahead and come up with an output. So it's much easier to do it that way. So this is what you actually hope to have in the real world. That's why computers are great, right? Why is a computer great? Because the very first thing you do is you convert to digital. And ones and zeros in digital world, there's no such thing as loading. So if you look at the world and what we're trying to do, you can massively simplify your design because now you don't have to worry about loading stuff. You just have a front end that converts everything to digital, and then you do your work in the digital world. We do that as much as we can in industry. It used to be these things in industry, they would be controllers, and you'd start putting a bunch of controllers on valves and stuff like that, and then things would start getting wonky. Now, when you have a digital controller, it just does all its processing digitally, and you don't even worry about it. So it makes things massively, massively more simple. So the world today is a lot simpler because of the digital, even though we make it more complex. And why is that? Well, because anybody here, you know, it used to be to change a generator is really easy. You just bump something a little bit and it would change. Now, I want to change something and I want to monitor 50 million other different things on a piece of equipment. So what ends up happening is now we're getting data overload, right? That's when we talked about on Tuesday with our car. When you get in a new car, and I only know this because my mom has a newer car, I think a 2023 or 2024, and you get into it and it's like, you know, they're older, they can't even figure out how to get the radio set up right. Bells and whistles, they don't know exactly what's going on, and it becomes information overload. So sometimes too much data is a bad thing.
But then that was the F5 and the serial just the car.
What's that?
They talk to your car.
Well, you have an assistant that you can talk to your car. But again, if you're driving down the road on the highway and you want an M4, so you're probably driving 90 miles an hour, right? You're just zipping along. There's a lot of road noise, right? It's hard for the vehicle to be able to hear you. And still, there's very specific things like Alexa, turn on TV. You know, you have to give it very specific commands. You can't say, hey, Alexa, find me a really good TV show that runs from 8 to 8:30 and centers on this. That's when you need to get more into AI, when you get that ability to understand and recognize speech. Here's another really important one. Let me erase this so we can see. And this is our feedback. And this is one of the more complicated ones. Not the more complicated, but one of the more important ones. Because if you do not have the feedback in the system, you basically have an uncontrollable system. And what I mean by that is that you don't directly control what's happening on the output. You're guessing as to what will happen, but the reality of it is that you don't exactly know what happens. So feedback is a way of telling you the output is this, and then you need to adjust your input signal so that you get the desired feedback. So like the thermostat is a perfect example. Is that a system with or without feedback? What's that? With feedback? The thermostat that controls the temperature in this room? Does that have feedback or not? What's the feedback? The room temperature. So you can have systems that you basically walk in and it's designed to output a certain amount of heat based on the room size and the average temperature. And you could do that. You could have a system that would work really well. You could even have a system that works based on the time of day as well as the day of the year. But the problem with that is that what happens like today, it's probably a lot colder than it typically is, right? It feels like minus or 5 degrees or something like that. So if normally the temperature in this room or outside should be 20 degrees, you'd be off by quite a bit. So the temperature would be quite a bit colder. So adding that feedback element in just by monitoring the temperature closes the loop. Okay. Most systems would be closed systems, which means they have feedback. If it's a cheap toy and you don't worry about it, going down the road at a certain speed, that's a different scenario. A lot of times too, we are the closed feedback. So if we're unhappy with something, right, you walk into a room and the temperature doesn't feel right, what do? Bump up your thermostat. See, Pat's old school. He turns the dial. I'm trying to get you into the 2000s.
They're still current.
Oh, they are? I thought with the Nest, everybody just logged in on their phone and turned up the heat that way.
No, it's too smart for itself, so it decides to turn down the temperature, so you gotta, if it doesn't sense any movements, you gotta go turn it up.
Oh, okay. I thought they were popular once, but now everybody just uses their cell phone, right? Logs in, maybe not. What's that? Getting them, yes. We're improving. Or you could just throw on a sweater, right? I mean, so here's our input, and notice in the previous blocks, our input was R that went to our first transfer function block. Now we call it E. Why is that E, not R? So Barzilai is correct. It's not just R because we're subtracting that fed back output. So we could call it R minus something. Why do we call it E? Looks like a symbol there. Okay, let's do the analogy of the temperature in this room. Let's say we want the temperature at 68, but the room temperature is 62. What would be the equivalent signal to our E of S? Here's 68, 62. What would be E of S? 6, right? What's another way to say that? It's the difference between 68 and 62, or the error. It's the error, meaning it's not at what you want it to be. It's actually something different. So from just a purely mathematical standpoint, we could call it difference. But from a processor controls perspective, I want it to be this and it's not that. That's an error, so we need to fix it. And most of the time, our R of S is not called our R of S. It's called our SP. What does SP stand for? Set point. It's your set point. That's what you want it to be. And then this is what you got. That's our set point. So our input to our first block is E. So you can see that my C of S is going to be equal to E times G of S. But I also have to bring back the output that is run through that feedback block. So now I got to subtract it. So now I have my C of S equals R times, or R minus CH times all of that times G. Do a little bit of multiplying and factoring. And here's my block diagram. We derived this once already in this class. But my transfer function is G over 1 plus GH. Okay, so we can replace all of this with this. And we'll do that a fair amount. All right, so now we want to try to monkey with things because sometimes we have summing blocks and locations that makes it very difficult for us to do some of these matrix manipulations, things in cascade, things in parallel, or more importantly, things in either feed forward or feedback. So what we want to do is we want to figure out how to move a summing block either to the left or to the right. So what we see is the output of our G is equal to R times G. Yes, sir.
Yeah. The first letter you use the sound. Second letter you use the R. The R. What the difference?
Same thing. A summing junction or an add is the same thing. I would have to double check in MATLAB and Simulink that the add might do one or two different things. Like it might do a vector addition or something like that. I'm not exactly sure. Where the summing junction is just adding them in time. So I'd have to double check, but you're better off to use the summing junction in this class. In a summing junction, you can add more than two in Simulink. Because if you look and if you double click on your summing junction, it'll actually have in a block, it'll have a plus and a minus. If you want more inputs, you just go plus, 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 minus, 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 and then it'll just go ahead and have as many inputs as you specified pluses or minuses. So you can add those to a summing junction without any problem.
Why do you get plus minus like this?
Because it could come back as negative feedback or positive feedback. We don't know. We're not sure. This is just writing it generically. All right, so our input to our summing junction is R times G. And our output, C of S, is R times G, either plus or minus your X value. I want to move my summing junction. So I'm going to move my summing junction to the left, but I still, for equivalency, want my output to be RG plus or minus X. Okay. So notice the X value in the output. Does it actually multiply? Is it multiplied by G? It's not. It's just RG plus or minus X, correct? So what if I move it to the left-hand side? And if I run it through here, will I still have this thing circulated? No, because then I'm going to have the G multiplied it. So how do I make sure that my output doesn't have X times G in it? What's that? Feedback, parallel. Because we know here, in this one, this would be R plus or minus XG, right? That's not the same as this. So how do we make sure that X doesn't multiply by G? Can we divide that by G? Or divide by G.
Why would you want to do that?
Because if I have a system where I take off, let's say I take off over here and do something in that direction, I won't be able to combine, I might not be able to combine blocks to simplify it. So there are times when I have to move my summing junction to the left or to the right to be able to use, like the feedback path or the feed forward gain, that type of stuff. Okay, so just divide by G. Nothing fancier than dividing by G. Now, if we move from, so this time we move from right to left. Now we're going to move from left to right. So this one, you'll see that R and X are both multiplying by G. So if I move in this direction, move it to the right, I got to make sure I multiply by G as well to get the equivalency. All right, so that was moving a summing junction, okay? A pickoff point is different than a summing junction. A pickoff point is different because over here, you can see that I'm adding or subtracting something to that point. Whereas a pickoff point is I'm just pulling that signal. Whatever that signal is, I'm pulling it out, all right? So I can see that my pickoff point is just equal to R times GS. Now, I still want R times G over here. I've moved my pickoff point from the right to the left. So what do I need to do to make sure that C of S is equal to R times G? What's that? I don't want to move it back to the right side. I want it to be on the left side. Yeah. Multiply by G. So if I'm taking off over here, all I have is R. I know that I have to multiply that by G to still get RG. So that's what I do there. How about the other direction? Can you give me a clue? Yeah, if I move my pickoff point to the other side of my block, at this point, this is R, right? If I go over here, this is R times G, correct? So I'd better divide by G, get the same equivalence. So here's the summary. So you got to be very careful about moving a pickoff point and moving a summing junction, okay? Those are where a lot of people get trapped and make mistakes. If you move a pickoff point, you got to make sure that you're at the right spot. If you're moving a summing junction, again, you just have to be careful about how you do that. So here's just kind of the thing. So the way you do it is you look at what you're trying to do. So you look at your original block diagram and what am I trying to do? I've got two blocks that are in cascade. So then you can go to the equivalent block and then you can use the equation. I have two blocks that are in parallel, or three blocks or four blocks. And the other thing too is another way to say that is blocks in parallel is also a forward loop. A loop that goes from left to right is considered a feed forward loop. So at that point, I'm going to sum these and then combine them over here. So what I've done is I've just eliminated this path, right? Because I've got two paths to get to the output. So I've eliminated that by doing that. Moving a pickoff point. If I want to move from here to here, I'm moving a pickoff point from left to right, or another way to say that is behind a block. So if I do that, I darn well better make sure I multiply the feedback path by 1 over G. If I move from right to left, or move the pickoff point ahead of a block, I need to make sure I multiply the feedback path by G. And then if I have summing junctions, so if I move it, if I move it to a point beyond the block, I have to multiply those by G. So I'm basically moving the summing junction from left to right. If I'm moving the summing junction from right to left, then I've got to go ahead and divide by that. This representation over here is just an alternative representation of if we had, you know, our H2 and our Y are at the same spot. You could go ahead and do it that way. Now, the reason why I said be careful about moving a pickoff point versus a summing junction is look over here. If I move my pickoff point from left to right or behind the block, I have to divide by G. If I move my summing junction behind that block, I have to multiply by G. So 1 divides by, 1 multiplied by, and that's where we make a lot of common mistakes is sometimes you multiply when you should have divided or vice versa. Okay, any questions on this figure? So it's a good sort of cheat sheet type thing where it has the summary of all the highlighted ones that you would need. Okay. All right, so let's do an example. So this is the case going back to Pat is, I don't want to move my pickoff point. Well, okay. So Pat doesn't want to move pickoff points, so go ahead and find the transfer function without moving any pickoff points. Because how do you combine this block here and this feedback block there? If I combine these first, remember what this transfer function is. It's just going to be a single block. Where do I pull that pickoff point from? Pardon? Well, no, what if I have a single block? Where does that pickoff point come from? Someplace in the middle of the block, right? That's not going to work. So as Amanda said, what I need to do is I need to move this line over here. The other option I could do, can I also move this over here? Either one would work. You'd get the same result. It just might make sense to move this line from left to right, just because you've already included the G4. You don't have to do that step again. Okay? Make sense? Because once you move either of those pickup points, then it kind of falls off, because what happens is if I move this over here, you think, hey, I can't combine those blocks, but this is a common node. I can move this anywhere here, so I can actually show the pickup point coming further downstream. You actually see that right here, right? You can see that those are essentially the same point, but I just drew H3 further away and further to the right, so that you can actually see, oh, I want to go ahead and include those. I want to do that block later. I'm going to move it outside. So once you're on a common connection point on a line, it's a common node, you're welcome to go ahead and move it to the left or right as necessary, as long as you don't move outside of move on the other side of a block or a summing junction, you're good to go. All right. Here's our pickoff point, moving. Oops, sorry. And to move that pickoff point, let's go back to our slides. And sorry, maybe what I'll do is I'll do this. I'll do the snipping tool. That should be enough. Hopefully it copied over. All right, so to move the pickup point from left to right, which item on this table do I need to take advantage of? I'm moving a pickup point from left to right. We're moving it behind a block. Item number 3, which shows that if I move it to the other side, I'm going to have to divide by whatever that gain was for that system. So I'm dividing by G4. Pardon? Way over here? That's just the output. That would just be the overall output if you wanted to combine those. Okay, so now which one should I combine next? This one, right? Because it's all nice and cozy. It's wrapped around 2 different feedback networks. So which of these is it? That's a feed forward loop. It's none of these, right? This is the one where you have to remember for feedback loops, right? If you go from left to right or right to left, it's very different. So if I go from right to left, that's feedback, not feed forward. They're not in cascade. So with that being said, what should this be if I combine those as one? Is it Yeah, so if you get confused, these two are in cascade with each other, right? So you multiply those two first. That gives you this element. And then you already know H1, but at this point, because it's positive feedback, right? This is the positive sign here. You have to make sure and it's 1 minus G times H. So each time, if you get confused, just redraw what you got. H1 plus minus, but this is plus plus, right? And that's what you're trying to put in your feedback path. So let me erase this again so that I don't, oh, I'm sorry, I cascaded those. When it's in feedback, it's H2 over G4. Should have done that first. Now we're going to collapse the inner feedback loop to this one. Combine those two. Now we have that.
Why?
Excellent question. Why is it subtraction? It is subtraction because G, H, summer, plus, plus. This is my output. We'll call it Y. We'll call this X. So remember what Y is equal to. Y is going to be equal to, let's do the easy one first, H times G. Then what comes back through here is Y times H times G. Correct? That's that fed back path and it's added. So now I'm going to move my Y's to the other side. Or minus, sorry, not plus. Really wish the erase button would work here. So this is minus. Now we factor out Y. And if you remember, my transfer function is the output over the input. What's the output, X or Y? So Y, what's the input? X is going to be equal to so it's just the algebra where you get the negative number. Just the algebra. That's nothing more than that. If it was plus minus, instead of having the minus over here, because you would add the Y, H, G to both sides when you did your algebra step, that's why you'd end up with a plus there. Swap it around.
So which means here is 1 plus minus, that's why when the H part is minus.
Correct.
So it's like this.
Yep, the sign will flip. Yep. All right, so now what's the next block we want to do? So if we want to be specific, let's dump the G2 into here. Because then we have a simple feed forward gain. And then let's combine those. Okay. Make sense? No, doesn't make sense, Pat?
No.
It's okay. Cool. You go from here, we combined it to here. Now, here's a suggestion. This is just a suggestion. You got fractions and fractions. Anytime you have fractions and fractions, you should always do common denominator. And you'll see a lot of stuff will cancel out here. They do get a little onerous, but what you quickly realize, if you put this under a common denominator of this right here, that term and that term will cancel out. Right? And also, you'll notice the G4 will cancel out with the numerator here. So you simplify things dramatically. Howard?
You simplify right now before you combine that set.
I would. I always simplify right then because I have less steps. Let me show you how I'd simplify it, because I'll just go ahead. Here's how I would do it. And again, this is just a suggestion. You can do it any which way you want. So as I said, fractions and fractions means you have a common denominator. So my suggestion is, let's do a common denominator. So I have G2, G3, G4, all over 1 minus G3, G4, H1. To put these all under a common denominator, I need to have 1 minus G3, G4, H1. Multiply that by G4, correct? That's the common denominator.
Yep.
So now, this is a 1 over here, so I need the whole kit and caboodle. Get the whole kit and caboodle. And then over here, I don't need anything else because I already have that in the denominator. So that becomes plus G2, G3, G4. And don't forget, I have an H2 up front over here. That's often people will forget that term. Now I'm going to invert and multiply, or actually before I do that, I'll probably just get rid of my G4 because that's in common there. I actually could have done that step here if I really wanted to. Maybe you could have done it then just to simplify it. So now I'm going to invert and multiply, and what I see is this and this will cancel. So I'm left with G2, G3, G4, all over 1 minus G3, G4, H1, plus G2, G3, H2. So you still have a lot of numbers in there, but way less than what you had before. So it's a little bit easier to manage, in my opinion. And this is the other thing too, when you do your block diagrams, as much as you can, keep them in G's and H's, because it just makes the algebra easier. Because keep in mind, G2 could be S plus 1 over S cubed plus 3S squared plus 7S plus 5, right? Now start multiplying a G2 with that and a G3 like that and a G4. You've got, you know, a zillion S's. It's very difficult to do the math. But if you just keep them as variables themselves and you multiply and divide, then you have to do it at the end, but you only have to do it once. And so usually it's a little bit more straightforward. So keeping them as variables makes it much, much easier, I think. All right, so we have to throw the G1 up in here. And we saw how that'll come through. Anybody want to confirm that this is what we just got on the slide? We just derived? Is this the same as this? Nothing up my sleeve, right? You see the work, so there's nothing there. So then I move my G1 in there. And now I just have one more. And I have that. You guys want 5 minutes to simplify this down, or is that an exercise in futility? It's good practice, that's why I would do it, but how about we'll give you 5 minutes, because also it'll slow me down a little bit. I know you all have a test on Wednesday, so I don't want to give you too much new material. So I'll give you 5 minutes, 8:45, to go ahead and see if you can simplify this down.
We get to what are we getting at this? Table.
You'll get the Laplace table. And
Well, we have to know how to just be able to convert back to back.
what's that? The Laplace table is what you do to get from the Laplace domain to the time domain or vice versa. But I'll include final value theorem and all that stuff. I think that's the only thing you'll need on this test, unless I'm mistaken. And Conlon went through some of the stuff yesterday in his review, right? So that was helpful.
Yeah.
Did anybody see I put the exam review up as well?
Yeah.
He did go over it, okay. I put that up there and I told him he's welcome to use that or not, so. Because we would do the same, or he can just do whatever he wants, so.
Yeah, we're good with one.
Okay, we have the servo motor, that's the homework problem, yeah. Yep. Did you find the exam review sheet helpful? I mean, it helped him a little bit, but was it good for you?
Yeah, we use that and then 50 problems on the right.
Okay. Well, the problem is like, people sometimes complain that I write too much in my exam reviews. Pat's nodding, but I've had multiple complaints. Can you be more succinct? And it's like, I'm trying to do 4 weeks of material here in 4 pages. It seems like it's succinct, but.
I mean,
Ah, there we go. That's Pat telling the honest.
I skipped to the bottom, the meat and stuff, looking for this, and then I work off of that.
Great. So what I need to do now is I just write what's going to be expected on the test. I don't have to do all that writing for all the.
Well, I'll look back through and find some good points.
Help me out, Pat. Come on, just say sure.
Wait, you read them? Yes. All right, then why you read them, then you can do it. Yes.
Fair enough. No, I'm, sometimes I'm not happy to do it because when I've been there for 2 hours writing away, it's like, oh, I'd like to be done, but if it's helpful, I mean, I'm fine to do it. That's a skill I should have told about life lessons on Tuesday, is make sure you know how to write. Boy, oh boy, if you can write, you can almost write your ticket in industry. I'm a relatively decent writer. I'm not great by any stretch. My wife says all the stuff I write looks like I'm rude, but it's technical writing. You get to the point. And it's so important in your professional careers to be able to write effectively. And it just takes practice. I was a terrible writer when I graduated from college. And like I said, now I have some proficiency in it because I've been writing for so long. It took a long time, but now I'm pretty comfortable with it. And the way you get to be good at anything is practice. Practice, practice, practice.
Yeah, and then also, me and Drew, we are planning to go to Dubai.
You're trying to go what?
Dubai, me and Drew, the graduation.
To Dubai? Are you crazy? You'd be going to Dubai in the summer. Wait 6 months. Go in the winter.
The police, they're driving Lamborghini in Dubai.
It's supposed to be a wonderful country to visit, but I hear it's not a good place to go in the summer because it's just so hot.
So,
But in the winter, that's supposed to be a lovely place to visit.
but then the police driving Lamborghinis.
Well, they drive Lamborghinis because everybody else has Ferraris and Lamborghinis. If you want to pull somebody over, you have to go as fast as they do. So,
They are really big, beautiful.
well, it's like anything, right? I mean, there's places that there's a lot of wealth and there isn't. So it's just some places are wealthy and some places are not. So usually you only see about the capital, is it?
Yeah.
Right.
But then would you plan to go there?
I would love to go to, but I have 2 little kids, which means I'm not going anywhere because I can't afford it. So
World.
last night was $60. No, it was $130 in activities for kids last night, just one night. So
Rocking kids.
they had 2 basketball practices. Well, each kid had a basketball practice. One kid had, it's called athlete development, and another kid had a tumbling class. Do the math.
The word is 75.
Well, hopefully if I do the investing, right, I won't have to. I'll be lucky to be alive at 75. All right, anybody get the answer?
You,
You got it? I'll give you 1 more minute. Just common denominators.
actually, the easiest way to do it. Not the thing that we did instead of one was in the very It's which faster.
The way they what? Pat did it?
On yesterday, so what you did is remove the domain of the top. You multiply at the bottom. You get become faster.
He multiplied the denominator or divided the denominator.
See the spot?
Yeah,
So 1/1. When we did one here, we multiply this thing here. You go, we get this multiplied by the. Take this, multiply the bottom.
isn't that the same thing though?
Yeah, it's 70, but it's just faster.
Is it? To me, it's the same thing, because if you notice, this here is the same as this. So if I multiply both sides or put it under a common denominator, it's the same thing.
Yeah.
I guess I'm just being more mathematically rigorous, the way that I'm saying it.
Right, the whole.
Right.
Oh, I can make a page.
Well, that's okay. I have it here for you. Anybody get this? Okay, much less difficult when you multiply things out. So that's one of the things you can be expected to do is be able to bring these down algebraically. So we talked about, in Laplace, if we stay in the S domain, there's less work, but sometimes it's still a fair amount of work. We've got complicated systems with, this has 3 feedback networks and 4 feed-forward networks. So you've got a lot of stuff to work on.
So, in a future test,
What's that?
in a future test, we get a system like that, and you want us to squish it down.
Yes.
Is it just gonna be squish it down to the G's and the H's, or are you gonna be G1 is S squared plus?
Well,
plus-
If you have a ton of blocks, then I would say this is fine. But if I say, hey, find the characteristic equation for something, you would need to get it down to the S's, but it wouldn't have 7 elements in it. Might be 2 or 3. You can also do this in Excel. I mean, in MATLAB. You can do symbolic processing in MATLAB too. I don't know if I'd recommend it, but you can do that here. Okay, so you can actually all do the combine and simplify in MATLAB. Again, you just have to have the symbolic toolbox in MATLAB to be able to do that.
All
right. MATLAB will do it for you. Yep. You just have to go ahead. So like over here, you have to be able to use the intelligence to come up with what H4 is. Right? You have to modify it by adding blocks. So that's why we combine this one to call it H4. See how there was a combination? We did the same thing for G5, which is we had to collapse this feedback loop. So we had to figure that out by hand. Once you got to that, then you can start using MATLAB a little bit, right? You can see it says simplify. So the thing about MATLAB is it's doing sort of that, common factors or common denominator stuff for you. So you can do it in MATLAB. Okay. But you still need to be able to do the individual steps and figure out what's going on. So if you want to check your work, go ahead and do that. All right, 5 minutes. Your turn. What's that?
What's class and slide, is it for today?
I put on Tuesday's lectures. We got sidetracked a little bit, so.
Table.
Oh, the table?
Yeah.
Yeah, I can't do both, but that's like the 5th or 6th slide.
Yeah, the sleeping.
Hmm?
Sleeping pool.
Yeah, but if I have this up, I can't have this up in the snipping tool so it's legible. So you'll have to go back and forth. But you really only have, you either got to move a summing junction and pick off points, you get to decide what you want to do. My suggestion is if you make, well, I'll give you a hint. If you do one step looking at this, technically there's only one step that you need to do before you can simplify it all down. Are you asking a question, Isaiah? I can't read this. Okay.
The fundamental, you think when you feedback, use the one minus one.
You go G over 1 plus or minus GH. Yep.
Now when you move forward, what do you do?
You just put them in parallel, so you add them together.
When is the feedback for?
No, it's either feed forward or feedback. So feedback is G over 1 plus GH. Feed forward is you add them together.
Or just adding them?
And the feed forward, yep. Whatever the one forward is plus the other forward is, you just add them together. That's in parallel. Give you another minute. All right, what you got? Anybody want to volunteer? Bracket G1 times G3.
Yeah, so bracket to one.
So what would you do to bracket them?
No. Of course, I just moved the.
This, the summing point? Okay, hold on.
It's not so good,
Yep.
and then you can up.
Everybody understand what he did? He moved a pickoff point, so the description is, he moved the pickoff point behind a block. So he moved this over to here. And when he did that, he needs to make sure he multiplies or divides. If you move it to the right, you don't get to multiply by G1, so you have to multiply by G1 over here. Yes, there are multiple ways. Yep, that was just one of the ways that Brasilia did it. And once you have that, now you have this feed forward, this feed back, and then you have one in cascade. That's one way to do it. Anybody have another way to do it? Sorry? Feedback for H1, you mean the pickoff point?
Yeah.
What'd you do?
Or
You moved it over here?
Yeah.
Yeah, that's okay too. That works fine. If you did it that way, what would you have to do? Well, no, if you moved it to the front of G1, so you moved your pickoff point in front of a block, it's 1 over G1. So that's fine too.
So, why do you, I wouldn't do that, I'll stay in mind.
Because over here, right, you are, so over here, right, this, we'll just call this X. And over here, this is X times G1, correct? So if I move my pickoff point from X to here, this is a G1 term, right? So I have to divide by G1 to go ahead and do that. If I move it over here, it's the same thing, right? I have X times G1, but I move over here, it's X. So I need to have a G1 over here to get XG1 on the output. Did I say those backwards? Oh, okay, sorry about that. Backwards. If you get stuck, go up to, sorry, it's gonna take a while to get there. Here,
yeah, that's not the slides.
it's not in the slides?
Yeah.
I'm not-
13.
I'll have to go ahead and double check to see why that's not there. This is not the slides? If it's not, I'll put it in. Or I'll republish it. But you can see if I move a pickoff point behind a block, I had to divide by G. That's what Barzilay did. He moved it from left to right. If I move a pickoff point to in front of a block, I have to multiply by G, right, to get the same results. So you can use this here. It's not in there? Okay. All right, I'll have to update it. I'm gonna do it this way. So I don't have to spend so much time hunting around. So either one would work. Did anybody end up with a final transfer function, or do you want to just do one? So, do it this way. Does anybody want to see it simplified? Do it on whiteboard. Oh, we're on one. All right, so you get to pick. Do you want to use Barzilay's method or Pat's method? Class decides. Doesn't matter to me. Pat's method? All right, so Pat suggested We have this. And we have, let me give myself a little more room. And I'm gonna put, I have to multiply by G1. This is plus minus. Then I've got my G1, G2. This takes off from, I can move this any place I want, right? So I'm gonna try to really make it obvious is what I'm trying to do. Does that make sense? I'm just moving it, kind of moving it over here so you can see like where I'm trying to set things up. And then here's G3. All right, so anybody have a problem that there's no gain right here? You have a problem with it?
I mean, get it.
What's that?
Get it.
It looks complicated.
There's no,
There's no feed forward gain. Can I just say that's equal to 1? Can make it equal to 1, right? I'm not changing it. I'm just differentiating that that's the difference in the summing junction and the output. So you can always put a gain block in there equal to 1. Doesn't change the end result. So the first, and these are independent, so you can combine this one and this one all at the same time. So what I have is I've got this block over here. Okay, this all combined is 1 over 1 plus G1 H1. Because technically now this is in the feedback path, right? It's not in the feed forward, it's in the feedback. So we had to move it over here. And then this other one, these two are in parallel, which means. What's that? Then I have that.
so you add 1.
Isn't this right here X? And right over here it's X G1, G2. And this is the, isn't that X? Don't I have to add the two together? I can't forget about it. It does get added in there. If I don't have the 1, then this would not exist, right? So now what I end up with is G1, G2 plus 1, all times G3. Anybody get that? That's okay. You don't have to be perfect. You'd be close. That's fine. All right. So I'm going to let you go here because I want to make sure when we get back from the test, I want to be able to go review this. I don't want to just present all this material. Then you have the test and you forget all about it because we won't cover this material back until a week from no, it'll be a week from Tuesday, right? Because the next class, we're going to do a review. Then we have the exam. Then we go over the exam on Thursday. Then we do this material. So it's going to be a week from Tuesday. So almost a week and a half. So that's why I want to save some practice problems, unless you want to go through and keep driving forward. It's up to you. Any questions from TV land?
Yeah, Paul, I was just wondering, if you were to do it the other way, where instead of moving that point back at the beginning, you instead moved the pickoff point in front of G1 to the other side of G1.
So
Right,
if we went,
how you kind of showed it first.
if we went this way,
Yeah.
yep,
Should you end up with the same simplified
yes,
transfer function? I assume so. Okay.
you should, yep.
But then it's that you have G1 top, G1 bottom, you take it from G5.
You have to do some simplifications, exactly. You have a little more algebra to make it work. You get to the same point. It is equivalent. It would just be a little bit more math.
Yeah, you're right.
Does that answer your question, Drew?
Yeah. Other than that, looks good.
Okay. You have a question, Isaiah? I'll stop recording, but I'll keep the class going only because I was just curious as to the people that went to the job fair yesterday. I just want to